Hi, welcome you all for the session Optimal Binary Search Tree using the dynamic programming. First, we will recall the concept of binary search tree. In the binary search tree, nodes in the left subtree always less than the root node, and the nodes in the right subtree always greater than the right subtree. Greater than the root node. Okay, so here each node may contain key values and frequencies in the binary search tree. Key values are given here, frequencies may given, may not be given sometimes. The time complexity for searching the key in binary search tree is order of log n, because here suppose I am searching the 100. When I am searching the 100, it will be compared with the root node. 100 is greater than the 12, so it will search the right subtree, it will omit the left subtree, so it will take half of the tree. That's why it is taking order of log n at worst case. Now when we are trying to build the binary search tree by using given three number of keys here, uh, how many possible binary search trees possible? So for that we are having the formula here: 2 times of n combinations of n, ncn divided by n plus 1. So when you are substituting the values here, you will get 5 number of possible binary search trees. Those 5 number of possible binary search trees are given here. Initially we are taking the 10 as a root node, then we are taking next value 12, which is greater than the 10, added as a right child. Then we are taking 20, 20 is greater than the root, so it is going to right subtree. Right subtree already having the child, so then it is compared with the 12. So 20 is greater than the 12, then it is going to the right child. So here 20 is added as a right child. Likewise, when you are taking another method, another tree, here 20 is considered as a first node root. Then we are taking 12, so 12 is less than the 20, so we are adding that 12 as a right child to the 20. Then again one more value 10, so 10 we are taking here, which is less than the 20. We are going left subtree, so left subtree already having the child, so we are comparing with this. So 10 is less than the 12, so it is not having any child as of now, so 10 is added as a left child. So like this we can construct 5 number of binary search trees. Here we have to calculate the cost for searching a key in binary search tree. So for that we will use the number of comparisons. The search key is searched by using the comparison of node values available in the binary search tree. Here the levels are used to calculate the comparisons. First, the root is having the level 1, then following levels are 2, 3, etc. So based upon that, in the tree 1, here we are trying to check the comparisons. For example, I want to search the value 100. So when I'm trying to do that, here 100 is compared with the root value, so which is greater than the 10, then it will go to the right subtree. So here one comparison over. Then next one is, here also we are comparing 100 greater than 12, second comparison is over. Then again we are going to, down the right subtree. 100 is greater than the 20, so third comparison over. Then again we are going down, but it is null, so it is stopped. So you look at that here, at the node 10 we are using one comparison, right? So with that we are taking one comparison at the root node. Then when you are searching to the next level, you are using two comparisons, so 1 and 2. Then when you are coming down in the 20, you are spending three comparisons. Okay, totally three comparisons. So like that, when your levels are increasing, the comparisons are increasing. So average comparisons are calculated here. So all three comparisons divided by total number of levels equal to 2. Like that, when you are taking the tree 2, here in the root we are checking here one comparison. If I am checking the 15, 15 is greater than the 12, so what will be happen? Get into the right subtree. Here also we are checking 15 is less than the 20, it will check the left subtree of the 20. Here it is null. So here one comparison, and here two and another comparison, 1 plus 1, 2 comparison. So at the place of 12, one comparison; at the place of 20, two comparisons. Suppose I am checking 3. Okay, if I am checking the 3, then it will check compare with the 12, right? So 3 is less than the 12, then it will get into the left subtree. Then 10 will be compared. 3 is less than the 10, then it will come to the left subtrees, but here it is null, so it will stop the process. Here also it is having two comparisons in the left subtree, right? So first this one comparison, and here another one comparison, so two comparison for the node 10. So average we are consuming here 1 plus 2 plus 2 divided by 3 number of nodes, 5 by 3 comparisons. Then for the tree 5, here when you are checking the search key, when you are comparing this, here on one comparison, here 1 plus 1 2 comparisons, here 1 plus 1 third one third comparison. So at the place of 20 we are spending one comparison, at the place of 10 two comparisons, at the place of 12 three comparisons. So on and average here when you are calculating, we are getting two comparisons. Like that when you are searching here also, you see here one comparison, here two comparisons, here three comparisons. Average we have to calculate this 6 divided by 3, two comparisons. Okay, so like that tree number 4 also, here one comparison, two comparisons, three comparisons, added 6 divided by 3, two comparisons. So here which is the optimal binary search tree? So from this you look at that whichever is giving you less number of comparisons, that will be your optimal binary search tree comparisons. So here tree 3 4 is giving two comparisons, tree 2 is giving 5 by 3. 5 by 3 means 1 point, here 6 something, 1 so here 2 6 something. So here two comparisons, so only the less value is 1.6. So this is the optimal binary search tree among this 5 number of trees. Based on this, we can define the algorithm for the OBST. Here, the tree has to be constructed to minimize the expected search cost for the key. The search cost is calculated by using the number of comparisons required to spend for checking the key in binary search tree. And here OBST is having nodes. In each node is assigned with frequency. Another terminology is called weight, that represents the probability of the key which is going to be searched. The expected search cost of each node is sum of the product of its depth, that is the level, and corresponding weight, that is called frequency, so which is represented here. So level is multiplied with the frequency, the product of level and frequency, then sum of these values, so that will be the expected cost of its children. So based upon that we have to calculate the cost for each and every tree. Here for that we need frequency and key value to determine the overall cost of the searching node. Then here keys are given and its corresponding frequency values, that is probability values, also to be used. Overall cost of each searching node should be less. Okay, that is the important one. We want to minimize the searching cost. The time required to search a node in normal binary search tree is more than the balanced binary search tree cost here. So here it should be that is balanced. How it is happened? It is happened due to the balanced search tree is having less number of levels than another binary search trees. For example, here in the previous slide we have, look at that, this is balanced search tree which is having less number of levels than other binary search trees. So that is the reason it will have most of the time it will have less number of searching cost will be less than the another binary search tree. Okay, thanks for watching.